So last class we ended here and we talked about how we might determine the rate law by the method of initial rates. We can use different ways we can use initial rates, but this was one way. If we have some reaction, in this case this is the reaction, we have it written as such. We do a series of experiments where we change the initial concentration of N2O5, get the kinetic profile, and we can get the initial rates. Now I talked about the fact that if you take a look at the kinetic profile very early in the reaction, so if we expand this region to here, we see that this is the kinetic profile on this side, and below is the line, the tangent line to that curve. That tangent line would give us the instantaneous rate. Now, as it turns out, if we go for shorter and shorter time scales, we're getting closer and closer to the instantaneous rate. But if we use a short time period, our initial rate, our average rate won't be that different from the initial rate. We won't have a huge error associated, and we can do the measurements. So quite often what we do is we don't bother trying to figure out what that tangent line would be. We just take the slope of an early part of the initial reaction, and we take that as our rate. So we use the average rate. We try and use as short a time scale as we can and still get good data. We take then that initial rate and we plot it. We can plot it against anything we want. In this case, we've plotted it against the concentration of N2O5, and we found that we get a straight line relationship. That tells us that in the rate law, the exponent would be 1 because of this straight line. If the exponent were something other than 1, this would not be a straight line. If the exponent were 2, what we could do is plot the initial constant rates versus the concentration of N2O5 to the power of 2, and then that would be a straight line. So you would just have to examine the rate equation. The rate equation equals rate equals some rate constant times the concentration of N2O5 to some exponent. And we're going to get a straight line as soon as we have that N2O5 to the proper exponent down here. Okay, so that's one way. But we've had to do a lot of experiments to do this. Now imagine we have a more complicated reaction. Let's imagine we have this particular reaction. Bromate reacts with a whole bunch of bromide and a whole bunch of acid to give us bromine and water. Now, we know, because we're chemists and we now know, that the rate law, it's not an elementary reaction. If it were an elementary reaction, this would be the rate. That would involve 11 molecules having to collide at one single instant in time, and that's just not going to happen. The likelihood of that happening is infinitesimally small. So we know that's not the rate law. How might we get the rate law without using that other method? We would do something similar. What we can do is, if I hold the concentration of these two things constant, but then change the concentration of only one reactant at a time, so as long as I'm just changing the concentration of these, this is constant, this is constant, this is constant, we can now tweak out the exponent for that one reactant that we're changing the concentration of. So that's typically, experimentally, how we would determine a rate law. And here's an example for this reaction. We've done a series of experiments, and notice now between these two experiments we've changed the concentration of bromate, but we have kept the concentration of bromide and our pH constant. So now we've only varied one thing. Now here's a particular, if you're good with math, this makes it a little easier. So our concentration of bromate has doubled. If the exponent were 0, that would mean that the rate wouldn't change, right? Because anything to the exponent of 0 is equal to 1. And we've kept these constant so we don't have to worry about them. If this was 0, the rate wouldn't change because that would become 1. What if the exponent were 1? What would happen to the rate when we double the concentration? So if we double the concentration and the exponent is 1, our rate should double. If the exponent were 2 and we double our concentration, what would happen to the rate? It would go up by a factor of 4, okay? Because the exponent were 2. What if we tripled the concentration? How much would the rate go up by? 2 is actually a bad example. Doubling is a bad example because 2 to the exponent is 2 is also equal to 2 times 2. Now, if we triple it, what happens to the rate? If we triple our concentration and the exponent were 2, what would happen to our rate? It would go up by a factor of 9, 3 squared, okay? So if you're comfortable with exponents and algebraic manipulations, chemistry is a lot easier. So I would advise you, if you're uncomfortable, practice. Do some practice with your math. So here we have a series of experiments where we've changed the concentration of one of the items in each of the experiments, of at least one, I should say. So if we take a look at these two experiments, we've doubled the concentration of bromate and left everything else constant, and our reaction rate doubled. Our reaction rate went from 1.2 molar per second to 2.4 molar per second, and then that thus tells us that that exponent is 1. We can then take a look at one of the other sets of reaction. We take a look at these two and we see bromate is kept constant, hydrogen ion concentration is kept constant, but we've tripled the bromide concentration. And look at this, we've tripled the rate. Okay, so that tells us that the exponent for bromide is also 1. Again, had that exponent been 2 when we tripled the rate, when we tripled the concentration of bromide, if the exponent were 2, that would have went up by a factor of 9, and it didn't. So the final set of experiments that we can compare are experiments 2 and 4, where bromate is constant, bromide is constant, but our hydrogen ion concentration has been doubled, and our rate goes up by a factor of 4. The fact that it goes up by a factor of 4 tells us that the exponent is 2. So this is a complex reaction. We don't know the mechanism just now, and we're not going to deal with that just yet. But that is now our rate law. And from those series of experiments, we can determine the rate law. So this reaction is first order in bromate, first order in bromide, second order in H+, and what's the reaction order overall? It's fourth order overall. The fact that it's fourth order also tells us that obviously it is a complex reaction, because we know fourth order elementary reactions would be so rare as to almost never happen in our lifetimes. And the other reason we know it's complex is because the stoichiometry and the rate law are different as well. As it turns out, there's another way of determining those exponents, and you can do it using this equation. And it doesn't matter whether you use the natural logarithm or log 10, because they'll end up canceling each other out. But I find you're much more likely to make a mistake punching all of this stuff into the calculator. If you can do the other method, it's easier. However, sometimes the other method won't work. For instance, when you have fractional exponents, it's less obvious what's going to happen to those concentrations. And so let's take a look at another example. And I apologize, I didn't have time to put the little boxes in to separate out each experiment. But if we compare experiment 2 and experiment 3, we keep the chlorine concentration constant, and we double the concentration of carbon monoxide. And when we look at the initial rate, we double the initial rate. So that tells us that the exponent for carbon monoxide is 1. Then when we take a look between experiment 1 and 2, the concentration of carbon monoxide are kept the same, but the chlorine gas concentration is doubled. And the initial rate goes up a little more than a factor of 2, but not quite a factor of 4. So that tells us that the exponent is somewhere between 1 and 2. If it were 1, the rate would double. If it were 2, the rate would quadruple. What would happen if it were 3? What would happen to the rate? It would go up by a factor of 8, because it would be 2 cubed, which would be 8. Okay, so it's somewhere between 1 and 2. But if we throw all this data, if we throw these concentrations in here, those rates in here, and do this, we actually end up finding out that the exponent is 1.5. Okay, so the order of that is 1.5 for that particular reagent, Cl2. Okay, so sometimes when we don't get an integer exponent, we probably easiest to just throw it in here rather than try and figure everything out. Now I'm going to switch gears a little bit, and we're going to talk about something called integrated rate equations. Okay, so we're going to talk about integrated rate laws or integrated rate equations, depending on the textbook you're using. We're talking about the same thing. But let's take a little look. Our rate law, we're going to do first order reactions first. So first order reaction, recall that A decomposes into products. And we're talking about an elementary reaction here because we're talking about a reaction we know follows first order kinetics. And our rate expression is equal to some rate constant K times the concentration of A. We could also put this in terms of the differential rate law, and that is equal to, equal to minus okay, that's the differential rate. Now we're going to use a little bit of calculus, and we're going to change our differential equation. We now have a differential equation, and we're just going to change that, and then we're going to integrate it. So for those of you who aren't in calculus, you don't have to worry about this. We're not going to expect you to be able to derive this, but we do want to show you where the equations come from. And for those of you who do know calculus, it helps because if you forget the equations, you can always derive them. So we're going to rearrange this into we're just going to do an algebraic manipulation. And all we've done there is algebraic manipulation. Now we're going to do a little bit of integral calculus, and we're going to integrate. So when we integrate both sides, we can take the rate constant outside of the integral. And we're going to integrate that. It's going to be a definite integral. We're going to integrate it from 0 to time t, and that's going to equal, and on this side, we're going to integrate from our concentration, our initial concentration, to our concentration at time t. Once we do that, I'm going to erase this because it's in my way. I'm just making sure I get this right. Because it's a definite integral, the constants all cancel each other out for those of you doing calculus. Now we have a new expression. This is the integrated rate equation, and we can manipulate this equation just like we can lots of equations, and we're going to manipulate it in different ways. We may want it in this form. And okay, now we can also get rid of this natural logarithm by saying that AT so I've taken the anti-logarithm of this side. I have to do the same to the other side. Does anybody know what this expression is going to be? Anybody that's in calculus? Okay, for those of you not in calculus, this appears like magic, but for those of you in calculus, it's not, where E is just the base of the natural logarithms, okay? E is 2.7 something, 2.7, and then it goes on forever, okay? So this is an interesting equation, but now we can typically, so these equations weren't very helpful because they can give us rate, but most oftentimes we're not really interested in the rate. The rate actually changes with time. It's not very informative. Usually we want to be able to figure out what the concentration will be after some time that the reaction has gone on, because maybe we want to know when it's completed, maybe we want to know when it's half completed. So we can now rearrange this into a form that's useful. So this is probably, in this regard, one of the more useful forms of this equation. We're also going to see that this can be manipulated one more time to yield something that's useful. So those four equations are equivalent. They're just expressed differently. One is, we go from one to the other just by doing algebraic manipulations. And those are, remember, for first order reactions. Recall what a kinetic profile looked like for this is the kinetic profile, and it actually follows that equation. We call this an exponential decay. Okay. If we watch the products, we would have an exponential growth. Well, we would have the mirror image of this. I'm sorry, this would just be flipped up. So this is an exponential decay. It follows this equation where this is t. A at any time t is equal to a naught times e to the power minus kt, where k is our rate constant and t is time. We have if we want to take that form of the equation, let's bring it down here. So we have minus kt equals ln A naught, oops, AT. Again, this is the expression that we're typically used to. So we're going to have ln, that's the one we want, AT is equal to minus KT plus okay, what kind of equation is this? It's not an exponential equation. What if I wrote this? Y equals mx plus b. What kind of equation is that? It's the equation for a straight line, right? So now we have another way of presenting our data. If we present it like this, we'll end up getting a straight line, where this will be the ln of our concentration at 0 time, and our slope will be equal to the negative rate constant. Okay, so now we have a convenient way of plotting our data, and we can directly get the rate constant out of it just from a plot. So we can use this equation to figure out the concentration at any time t. If we have some problem where we know the rate constant, we know the amount of time, we can figure out the concentration at any time t. And if we know a bunch of concentrations and time data, we could plot it and then fit a best line to our equation and take the slope of that line and figure out our rate constant. So we have experimental methods to do two different things. Scientists quite often like it when they can manipulate an equation to get it into a straight line form, because as human beings we can plot data and we can very easily tell if it's close to fitting a straight line. So now we're going to do an example, and I'm going to do it down here, so I'm going to erase all these. Yeah, I'll erase all these. I have to draw them again, but. So if you've downloaded the slides, you know this problem. We have some pesticide, and we know the rate constant for the decomposition of that pesticide in the atmosphere, in the environment. At 25 degrees, the rate constant for the first order decomposition of some pesticide solution is 6.4 times 10 to the minus 3 minutes to the minus 1. I've put the pertinent data over there. If the starting concentration of the pesticide is 0.314 molar, what concentration will remain after 62 minutes at 25 degrees? So if we take a look over there, we see that we know our rate constant, we know our time, and we know our A naught. What do we want? We want to figure out the concentration of our pesticide at some time t. And we'll just use this expression as the easiest one to use. Okay, so we know this, and that's 0.0314 molar, I believe. Yep. Our rate constant is 6.40 times 10 to the minus 3 minutes to the minus 1, and our time is 62.0 minutes. A couple of things to note here. Well, one thing to note for sure. What happens to the units up here? We have minutes to the minus 1 and minutes. So what happens to our units there?
They cancel out.
They cancel out, that's right. Typically when you have something with an exponent there, it's a little bit more satisfying when those units cancel out. Otherwise it's what do you deal with units in logarithms and everything. So those cancel out. These units stay. Something else we know when we have a decomposition reaction. What do we know? Actually, for any reaction. We know that at time 0, our initial concentration of reactants, after some amount of time, we know that we're going to have less. So when we do these problems, one of the things we want to make sure of is that the number we obtain for some concentration of a reactant after some period of time should be less than the initial concentration. So if that's not the case, you've done something wrong. But we can plug all these things in, and I won't bother doing it. And that equals 0.0211 molar. We just have to plug all these in. Very simple problem. You make sure you know how to use your calculator. If it comes time to test time and you have to borrow a calculator, try and be early so that you can figure out that calculator just in case it's differently than yours. But you need to know how your calculator deals with this thing. It will either have an e to the x, in which case you multiply these two out, throw that into your calculator, or it may call it an anti-log. So just figure your calculator out. In terms of up there, notice all the different algebraic manipulations we did. It's very advantageous in chemistry if you're pretty good with algebra. And so if you're not, this semester we're going to see a lot of algebraic manipulations. So you may want to go back and practice your algebraic manipulations, just so that sometimes things don't appear to come from nowhere. Sometimes I may skip a couple of steps. Feel free to ask, but be comfortable with your algebraic manipulations. The next thing I want to talk about is half-life. Okay, and the half-life for any reaction is simply so in other words, when A naught gets reduced to 0.50, the amount of time is the half-life. The amount of time for this to be reduced to half of its value is the half-life. We're going to now do a few more algebraic manipulations. Oftentimes, we can talk about a reaction in terms of its rate constant, but what you will notice is quite often, particularly for first-order reactions, people will talk about a half-life instead of a rate constant. So, let's remember our expression, ln. Okay, now we're going to use this expression. We want to figure out the half-life. So what do we know about the half-life? What is AT at the half-life? We know that the concentration at time t after one half-life is going to be half of the concentration of the initial concentration. And this is still going to be equal to minus kT, okay? Our A naughts will cancel out, and we end up getting, oops, I'm going to put T half here. Try to put T half there. Okay, so at T1 half, our concentration of our reactant is half of what it was at the beginning. We can now change this. We're going to do some manipulations. We're going to flip T1 half over here, and this is going to equal okay. The A's canceled, the A naughts canceled out, and that remains, and we've just switched our logarithms around. We want to do one more thing, and this appears to come out of nowhere, but it doesn't. Oops. Okay. How many people understand where that 2 comes from? Okay. If not, it's okay. It's just being comfortable with logarithms. The natural logarithm of 0.5 is actually equal to the negative of the natural logarithm of 2. Okay, so we just changed we got rid of the negative side by converting that into the natural logarithm of 2. And as it turns out then, we're now going to for a first order reaction, the half-life is equal to 0.693 divided by K. Okay? For first order reactions, it's relatively easy. The half-life is approximately 0.7 divided by K. If we were to put our now the nice thing about a half-life for a first order reaction, this is A naught when A naught gets reduced by half. Okay, this is 1 half-life, and this is equal to, actually, I'm going to do it this way. If we reduce this by half again, it'll be another half-life. Two half-lives, and this is actually equal to 1/4 A naught. If we reduce it by half again, okay, this works for first order reactions only. It doesn't work for other orders, but for a first order reaction, the half-life remains the same throughout. So once we've divided it in half, for it to be reduced by half again will be another half-life. For it to be reduced by half again will be another half-life. This relationship holds for first order reactions. We go by half, quarter, an eighth. The next half-life will be reduced to a 16th, then a 32nd, and so on. Okay, now I'll erase this and got that. Now we're going to deal with second order reactions and their integrated rate equations. So in this case now, our second order reaction is going to be A plus A goes to products. And in fact, we could also put this as 2A goes to products. And then our rate is simply K. It's now a second order reaction. What's my rate law going to be? Rate equals K times the concentration of A to what exponent? 2, that's correct. And what's our differential expression for this reaction? It's going to be minus 1/2 d dA dt. Okay, so we're going to do the same thing now. We're just going to set it up and do the integration. We're going to do an algebraic manipulation here. Because these two expressions are equal, we're going to take the half. We're going to get rid of the half and put it on this side. That gives us minus 2k. And we're going to take our dt. And that's going to equal 1 over a squared dA. We're now going to do our integration. We can take all the constants out of the integration. And we get over to here. I'm going to now move over here. So we have minus 2k t is equal to minus 1 over a t. Okay, and that's not really very convenient just yet. I'm just going to switch things around. I'm going to switch these two around, and we have 1 over That's the most useful form of this integrated rate equation. And so if we take a look at the exponential to k, for a first order reaction it looked something like this. For a second order reaction we would start with the same concentration. And it would look something like this, okay? So this is first order. And the one on top is second order. And it's hard to tell by inspection that one is first order and one is second order. We could fit them to their actual decay types of orders, but one of the things that's nice about that equation let's put our equation right here. 1 over what if instead of plotting the concentration versus time, I were to plot, 1 over the concentration versus time. Taking a look at that equation, we can see that that's going to be a straight line. Our slope is equal to 2k, sorry, and our intercept is equal to 1 over a naught. So we now have a convenient way of plotting a second order reaction of the type A plus A goes to products. As it turns out, we'll talk about it next class actually, and we'll talk about it, we won't do it. When you go from A plus A goes to products to A plus B goes to products, the rate equation gets tremendously complicated, so you won't have to worry about it. But as chemists, we have a way of dealing with that complexity. We're in control of the starting conditions of the reaction, and when we're looking at the kinetics for a reaction of the type A plus B goes to products, we make sure that the initial concentration of A equals the initial concentration of B, then it reduces to this form, and it's easier to deal with. And you won't deal with that until you get into, I believe it's third year phys chem, for those of you who go that route. So that's our integrated rate law for second order reaction. Second order half-life. How much time do I have? I'm actually going to stop there. You guys get out a little earlier because I ended the previous class at that slide, so I want to keep you guys in sync.